Good morning, everyone. So I will introduce in Thai first, and then I will introduce this event in English. This event will be recorded in Zoom. Just let you know. สวัสดีทุกท่านนะคะก็ขอบคุณทุกท่านนะคะที่มาเข้าร่วมในเวิร์กช็อปในครั้งนี้นะคะก็ชื่อผู้ช่วยศาสตราจารย์ดร.กรวิก ตนักสรานนท์นะคะก็ตอนนี้เป็นอาจารย์ประจำอยู่ที่ภาควิชาวิศวกรรมสำรวจคณะวิศวกรรมศาสตร์จุฬาลงกรณ์มหาวิทยาลัยค่ะก็เป็นผู้ร่วมจัดงานนะคะก็จะขอกล่าวถึงที่มาของงานนี้นะคะแล้วก็จะแนะนำสปีกเกอร์แต่ละท่านนะคะงานนี้นะคะได้รับทุนสนับสนุนจาก University College London นะคะที่เรียกว่า Global Engagement Fund นะคะโดยทาง UCL นะคะมีเทคโนโลยีปัญญาประดิษฐ์หรือที่เรียกกันว่า Artificial Intelligence นะคะสำหรับการหาปัจจัยที่ทำให้เกิดอุบัติเหตุจักรยานในลอนดอนนะคะซึ่งก็จะเป็นจักรยานแบบปั่นๆนะคะซึ่งในประเทศไทยเราอะค่ะก็มีอุบัติเหตุมอเตอร์ไซค์เยอะมากนะคะถึงแม้ว่าปัจจัยของจักรยานกับมอเตอร์ไซค์เนี่ยจะแตกต่างกันนะคะแต่ก็น่าจะสามารถประยุกต์ใช้เทคโนโลยีดังกล่าวได้นะคะซึ่งหลังจากเวิร์กช็อปนี้ก็จะเป็นการทำวิจัยต่อไปนะคะซึ่งจะมีอยู่2ส่วนนะคะก็คือการทบทวนวรรณกรรมที่เกี่ยวข้องเกี่ยวกับอุบัติเหตุมอเตอร์ไซค์ในประเทศไทยนะคะโดยการสัมภาษณ์ผู้ที่เกี่ยวข้องนะคะที่เกี่ยวกับอุบัติเหตุมอเตอร์ไซค์นะคะแล้วก็การทดลองนำวิดีโอจากกล้อง GoPro 360 องศาที่ถ่ายในกรุงเทพเนี่ยมาทดสอบวิเคราะห์ข้อมูลด้วยเทคโนโลยีปัญญาประดิษฐ์ค่ะสำหรับสปีกเกอร์ในวันนี้นะคะท่านแรกก็จะเป็นศาสตราจารย์ดร.เกษมชูจารุกุลนะคะท่านเป็นอาจารย์ประจำคณะวิศวกรรมศาสตร์จุฬาลงกรณ์มหาวิทยาลัยนะคะท่านเป็นผู้จัดการศูนย์ความเป็นเลิศไทยแรปนะคะแล้วก็อีกท่านหนึ่งจะเป็นอาจารย์รองศาสตราจารย์ดร.มงคลเอกปัญญาพงศ์นะคะอาจารย์ประจำสถาบันเทคโนโลยีแห่งเอเชียนะคะซึ่งท่านได้พัฒนาระบบ AI สำหรับความปลอดภัยทางถนนนะคะส่วนผู้เชี่ยวชาญจากประเทศอังกฤษนะคะซึ่งจะมาพูดในช่วงหลังจากเบรกนะคะก็จะมี Professor Nicola Christie นะคะท่านเป็นศาสตราจารย์ด้านความปลอดภัยทางถนนนะคะแล้วก็เป็นประธานของ London Road Safety Council นะคะรวมทั้งเป็น Fellow ของ Charter Institute of Highway and Transportation นะคะและเป็น Parliamentary Council นะคะหรือเป็นที่ปรึกษารัฐสภาด้าน Transport Safety นะคะถ้าจะมาพูดเรื่อง using data to understand safe systems for pedal cyclists นะคะและ Professor Bani Anvari นะคะท่านเป็นศาสตราจารย์ด้าน Intelligent Mobility และเป็น Touring Fellow ที่ The Alan Turing Institute นะคะท่านจะมาพูดในเรื่องของ Orchestrating Safety and Serenity with Autonomous Vehicles นะคะโดยจะพูดร่วมกับสปีกเกอร์อีก2ท่านนะคะสุดท้ายนะคะจะเป็นรองศาสตราจารย์ดร. เจมส์ ฮาวเวิร์ธนะคะท่านเป็นอาจารย์ประจำภาควิชาCivil Environmental and Geomatic Engineering หรือที่เราเรียกกันย่อๆว่า CEGE นะคะที่ University College London นะคะก็จะพูดถึงงานวิจัยอุบัติเหตุจักรยานในลอนดอนแล้วก็จะมีคุณณัชพลจงวิริยานุรักษ์นะคะนักศึกษาปริญญาเอกที่ UCL ก็จะมากล่าวถึงโครงงานประเมินความเสี่ยงจากภาพวิดีโอแบบพาโนรามาโดยใช้เทคโนโลยี Image to Text แล้วก็ Large Language Model นะคะหรือที่รู้จักกันในชื่อของ ChatGPT นะคะทั้งหมดนี่จะเป็นการบรรยายแล้วก็จะมีพักครึ่งอาหารว่างนะคะในช่วงเวลา 3 โมงถึง 3 โมงครึ่งนะคะก็หลังจากจบเวิร์กช็อปนี้แล้วก็จะมีอาหารเย็นที่เริ่มในเวลา 5 โมงครึ่งค่ะหลังจากนี้จะเป็นการพูดภาษาอังกฤษทั้งหมดนะคะเนื่องจากมีผู้ฟังทางอังกฤษด้วยต้องขออภัยมาณที่นี้ด้วยนะคะ Good morning all attendees. It gives me great pleasure to welcome you to our Thai UK workshop on AI for traffic safety analysis. This workshop aims to share knowledge and lesson learned between UK and Thailand on AI for traffic safety. Before we get started, may I thank Global Engagement Fund, University College London. May I thank all of our speakers for taking part in this event to share their knowledge and experience. It's now my pleasure to introduce our first two speakers, Professor Kasem Choocharukul, ThaiRAP lead, to talk about road safety in Thailand and ThaiRAP. Then I would like to invite Associate Professor Mongkol Ekpanyapong from AIT to talk about his work on AI road safety applications in Thailand. Professor Kasem, you can take it away.
And good morning, our colleagues and friends from the UK. Thank you very much for the introduction, Dr. Garavig. My name is Kasem Choocharukul. I'm actually a professor at the Civil Engineering Department at the Faculty of Engineering, Chulalongkorn University. And at the same time, I'm leading the Thailand Road Assessment Program, or shortly ThaiLAP here in Thailand. I have about half an hour to speak today, and what I would like to cover is the overview of the road safety situations. Especially this is good for those of you who are in UK and you might not be familiar with the Thai traffic situations. And then I will briefly discuss about the Thai Road Assessment Program. And in essence, I also would like to talk about the potential of using the artificial intelligence data in order to be applied for the Thai roads. So let's get started. These are the three things that I would like to cover today. First of all, before getting into details on the traffic situations, the road safety situations in Thailand, it's good that we all understand and we are on the same page in which we understand the safe system approach. This is not new, I would say, and every country has already embraced this kind of concept. We believe that the death and serious injuries from the traffic crashes are unacceptable. So we know that humans could always make mistakes. So that's something that we have to keep in mind. And humans are vulnerable. So if we have a crash or some crashes happened, so humans can tolerate to some extent. We are vulnerable. And the responsibility due to the road accidents, it is being shared. We cannot just blame to the drivers or to the traffic engineers or to the road agencies, but it's everyone's responsibility. Therefore, when we talk about the road safety, this is the proactive approach. So we have to consider many components. As you can see from this figure, we are looking for the safe roads, safe speeds, safe vehicles, and of course, safe people. So this type of thing have been accepted worldwide, and it's being known by the safe system approach or safe system concept. And according to that, the UN, the United Nations, has recently set the goal. We call it the Global Plan under the decade of action for road safety. That's another decade, I would say, because it has already been set a decade ago from 2011, 2020. But now we are in the second decade of the action for road safety from 2021 to 2030. And of course, we mentioned about the safe system approach already. Our goal worldwide is to cut the road crashes by half or at least 50%. This is a very challenging goal, especially for Thailand, because so far we have not yet achieved this kind of goal at all. So I will show you some more details and examples later on. And if you can see here, to achieve this goal, there are 5 components on the left-hand side. We are looking for the safe road infrastructure, of course, the safe road use, the multimodal transportation and land use planning, the safe vehicles, and lastly, the post-crash responses. So this is something that we can do. As a traffic engineer myself, I would focus on the safe road infrastructure. And if we look at the Sustainable Development Goal approach, or the SDG, you know, there are many goals here. When we talk about the global road safety targets, it is related to these 2 goals, that SDG number 3, particularly 3.6, and SDG number 11, that's for the sustainable cities and communities. We are looking for the SDG target 11.1. And at the same time, the World Health Organization, or WHO, has also set the global road safety targets for 12 components. I would like to highlight these 2 components, that is the target 3 and 4. They are particularly related to the roads and highways. By saying target 3 here on the left-hand side, at the end of the decade, we would like to have all new roads being safe. That means they will achieve the technical standards for all road users. So in technical term, we are looking for the 3-star roads. That's considered a safe road for the new one. Likewise, on the target 4 on the right-hand side, by the end of the decade, we love to see more than 75% of the travel on the existing roads. This is where we are traveling at this moment. They should achieve and meet the technical standards. So this is a very challenging goal again, but these are the 2 targets being set by WHO under the roads and highways. Now, looking closely at the statistics in Thailand, I'm showing you here the crash statistics from 2011 up to last year data. You can see here that it's very high and pretty much constant across the decade. From 2011, our road fatalities were more than 20,000. Looking at this number, it's very high. Consider the population of Thailand. That means every day, I'm saying every day, almost 30 or 40 people die on the roads. Every hour, we have about 2 or 3 fatalities. Every hour. And that happened every hour, every day, every week, every month, and every year. Since we have this kind of data. Up to now, you might see some drops here during 2020 up to 2022, but that's something related to the COVID-19. The pandemic reduced our travel, so that's why we have a drop in the road fatalities. But overall, I would say that we are not improving in Thailand. The statistics clearly show that the road fatality trends in Thailand is, you know, almost constant. And even though we have put a lot of investment, we have put a lot of countermeasures there, but we don't see any improvement in terms of our road safety condition. Comparing Thailand with other countries in ASEAN, our rate, this is the number per 100,000 population. is the standard rates. When we talk about the road fatality rates, Thailand is number one in ASEAN. We got around 32.7 deaths or fatalities per 100,000 population. That's the highest. And if we compare to the right-hand side, the world average is just 16. So we are almost double than the world average. Comparing with the ASEAN average, 18 only. So in Thailand, so that's considered very high, 32.7. So this is from the WHO data. Now, looking more closely on the fatalities, if we separate it by the vehicle types, you can see from this slide that 74% of the deaths are due to motorized 2 and 3-wheelers. So that's motorcycles, as we know. So out of 100 crashes in Thailand, 74% can be blamed by the motorcycle users. But if we look at the registered vehicles, motorcycles are accounted for only half of 55%. So this number is really overrepresented in terms of the deaths from motorcycles. So that's something we have to keep in mind. And this signifies the importance of road safety, especially for the motorcycles. We have a lot of deaths from the motorcycle users here in Thailand. Now, looking on the other hand, in terms of the road infrastructure network, in Thailand, we have around 700,000 kilometers of the road network, and it belongs into 2 ministries. One is under the Ministry of Transport, so they are responsible for the Department of Highways and Department of Rural Roads. On the other side, that's the Ministry of Interior. They are responsible for the local roads, including the one under the Department of Local Administration, Bangkok, or BMA. So these are something under the Ministry of Interior. So in total, that's 700,000 kilometers of the road network. But for the main highways, if you look at the roads under the Department of Highways, that's around 50,000. So this is the principal arterials, the major arterials, the road that carry a lot of traffic in Thailand. That's under the Department of Highways, and it's accounted for around 51,000 kilometers of the total road network. Now, coming to the ThaiRAP, before we talk into ThaiRAP, everyone should understand what the ThaiRAP is. ThaiRAP stands for the International Road Assessment Program. This is the registered charity. So it is a non-profit organization, and we are looking for with a vision for a world free of high-risk roads, and it's being supported by many agencies. Mainly the FIA Foundation, and the responsibility of the ThaiRAP is to assess the road conditions in terms of the road infrastructure. And so far, more than 100 countries have already incorporated this idea, the ThaiRAP, the star rating assessment for their road assessment in their own country. And we have been assessed a lot of kilometers of the road highways under this program. And you can see that in addition to ThaiRAP, we have some country with the RAP. That's the local identity under the ThaiRAP. And we can see here, ThaiRAP is one of them here. In Southeast Asian, we have the ThaiRAP, that's the Thailand Road Assessment Program, and the MyRAP, that's for Malaysia. ThaiRAP started actually in Europe from 1999, and then we have the OzLab in Australia, US Lab in the United States, GiveLab the New Zealand, and then the ThaiRAP is actually established in 2006. And then up to 2012, up to 70 countries worldwide have incorporated this concept. ThaiRAP actually started in 2018 by the Faculty of Engineering, Chulalongkorn University. So we work with ThaiRAP and the Department of Highways, as well as the Department of Rural Roads and the Bangkok administration. We work together under a funding, and we set up the ThaiRAP happening during that year from 2018 onwards. As I said, up to now, more than 100 countries worldwide have used this kind of load assessment concept to evaluate their load safety condition. Well, when we talk about the load safety assessment, under the ThaiRAP, the core is to make to evaluate the road under the ThaiRAP star ratings. So star ratings is something based on the road inspection data, and it provides a simple and objective measure. Sometimes when you are being asked how safe is your road, it's very hard to tell if you just look or evaluate by yourself. Under the same framework, that is the ThaiRAP framework, everyone can have the same standards, same specifications, same rules in order to assess the road condition. So under the star ratings, 5 stars mean the low risk roads or the safest road condition. And on the other hand, 1-star road, that's the most dangerous roads or the high risk road. So that's why this kind of concept is really easy to understand to even general people, because when we go book the hotel, you would like to love staying in the 5-star hotel, and when you go to the restaurant, you would love to go to the 5-star restaurant. Similarly, when we are traveling or when we are driving on a highway, we love to drive on a safe road that is the 5-star road condition. So that's simply the basic concept of the ThaiRAP star ratings. The good thing is that we are not going to assess vehicles. In the past, when we constructed the road, mainly we look at the design, the geometric design, and the data, focusing on the vehicles only. But in terms of the ThaiRAP star ratings, we also focus on the vulnerable road users, and they are motorcyclists, pedestrians, and bicyclists. So they are also important, especially in the urban setting where we have a mixed use of cars, motorcycles, bicycles, and people walking along the sidewalk. So when we assess the road condition there will be 4 versions under one road. 1 version, 1 star rating, 1 set for car, 1 set for motorcycle, 1 set for pedestrian, and 1 set for bicycle. So that means a road that is being designed safely for vehicles might not be safe for pedestrians if we don't consider that component. By achieving our goals that I said earlier, we are aiming for the road with the 3-star for all road users. So that means we want to see a road for 3 stars for cars, 3 stars for motorcycles, 3 stars for pedestrians, and also 3 stars for bicyclists. So that's simply the basic concept of the ThaiRAP star ratings. In addition to the star rating, we also perform the risk maps. So this is based on the crash historical data, so we can see which area and which road network is dangerous, which one is already safe. I will also consider the investment plans. Given the road condition that we have assessed, what would be the good countermeasures in terms of economic effectiveness, in terms of the investment, in terms of the, let's say, benefit cost ratio. If you spend $1 or 1 baht, what's the return in terms of the investment plan here for the road safety? We also consider the performance tracking from past to present and to the future in terms of the target setting. What should be our standard in terms of the road safety? So this is something that we call it the ThaiRAP protocols. Let me explain a little bit more on the ThaiRAP or the Thailand Road Assessment timeline. It started in 2015. At that time, we evaluated the road network in Phuket Island or Phuket Province. That's being done by AIT, Asian Institute of Technology. And then during 2016, we got the budget from the Bloomberg Philanthropies budget. and we work together with the Bangkok administration, focusing on 3 areas in Bangkok. That's basically the start of the ThaiRAP program here. We focus assessing on Sirom Road, Yaowarat Road, and Asok Montri Road at a time. And then we further extend our collaboration with other road agencies in Thailand, like the Department of Highways, the Department of Rural Roads, and we conduct up to now more than 1,000 kilometers of road assessment already. And you have seen the figure above already. That's the ThaiRAP being part of the regional road assessment programs. And on the lower part here, our Faculty of Engineering, we are honored to be one of the IRAP Center of Excellence, along with other road research agencies. In UK, that could be the TRL, and we have some other road agencies also being part of the what we call the IRAP Center of Excellence. So this is the identity that will look at the model inside how we assess the loads, what are the important variables, and how impact those variables are for the road safety risk. So that's it's our honor to be there as the one of the IRAP COE also. So from the past up to now, we have performed trainings and capacity buildings, as you can see from these photos. And then we have a lot of sessions going on, like introduction to IRAP, the IRAP assessment, how to manage the IRAP projects, how to perform the IRAP star ratings and safer road investment plan, and so on. We also introduce the road safety audit to the officials under the road agencies in Thailand. Like this one, we have the session on the road safety audit for people under the BMA, the Bangkok Metropolitan Administration in the past. And we also have collaborations with other related road agencies. In Thailand, we work with some other universities as well, like Chiang Mai University, AIT. For the government part, we work with the Department of Rural Roads, Department of Highways, the Bangkok city. Internationally, we work with the MILOS, which is the Malaysian Institute of Road Safety Research. That's under the ministry, the government part in Malaysia. We also work with ChinaLab. That's the road assessment program established in China, and similarly in India Lab also. So that's our collaboration so far. Now, let me go into more details on how we assess the roads. Given one figure, like what you are seeing here, it's a typical urban setting in Bangkok. Actually, it's just in front of our university, Chulalongkorn University, in the middle of Bangkok, Thailand. It seems to be perfect for everyone to dive. But if we look closely at the components, the engineering components that could contribute to the road safety, you can see that I highlight something in red. That means these are some of the risk components. For instance, we still have the property access. People can just suddenly move or drive from the roadside and then merge with the main road. We have some obstacles like the big trees on the roadside. That's very dangerous when you hit it by the car. Speed limit is one of the concerns in Thailand. The speed limit for the city area, for the municipal area, it's being set at 80 kilometers per hour by law. So that's considered very high, and we would like to reduce this also. But if you don't see any speed limit sign in the city, it can be up to 80 kilometers per hour. So that's really dangerous. And the box in yellow, that's something almost risky. And the green are something that is already good. Like here in this figure, we have pedestrian fencing, we have pedestrian crossing, the pavement condition is good, the lane width is wide enough to dive, and so on. So when we look at this and we try to assess for the star rating, we would think about those 4 versions, one for car, one for motorcycle, one for bicycle, and one for pedestrian, and evaluate it according to the IRAP specifications and come up with the star rating for this particular section of the highway. Similarly, when we travel out of town, let's see a typical setting in rural roads in Thailand. You can see, for example, in this figure, it's a 2-lane highway. Seems to be good, but a lot of situations, a lot of components that we have to keep in mind. For instance, the sight distance may not be that clear enough. The speed limit, in the previous slide, I said that in the urban area, that's 80. Even worse, in the urban area, in the rural area, outside municipal areas, the speed by law can be up to 90 kilometers per hour. So let's imagine if you have a crash and you drive like 100 kilometers per hour, the fatalities might be very severe. You can see that there are some big trees alongside in the shoulder area. The downward slope is not good. There's some property access here. The median center seems to be good, but this is very much prone to the head-on collision. Imagine that the vehicle on the opposite direction, where the driver may fall asleep and then they may cross the median center line and hit you also. So it's better to build with the median concrete than just the painting like this. So this is considered not that safe. Well, in terms of the result, as I said, we have also already surveyed some of the highways and roads in Thailand based on the IRAP star rating concept, and mainly in Bangkok area and also in Phuket area here. You can see by the colors of this mapping, green representing 5-star. You don't see any green or not at all green here. 4-star represented by yellow, 3-star the orange color, 1-star black, and 2-star red. So you can see that most of the highways in Thailand are not that safe. So this is the evidence base. In the past, we may not know, or we will just tell, well, it's not safe, but we don't have any evidence. But based on the assessment, which is consistent across all countries in the world, this is something that we found. It's still not safe. Look at the map closely. I separated by user types. On the left-hand side, you can see that up to now, based on our finding, our inspection, 60% of the travel is still unsafe. When we say safe or unsafe, we cut off at the 3-star. So 60% still under 1-star or 2-star. They are not that safe, even though, you know, we build the road for the vehicles, but the existing infrastructure still not safe, even for the drivers, for the vehicle drivers. On the right-hand side, it's even worse for motorcyclists. We have to admit that in Thailand, we don't have much facility to accommodate motorcycle users. So that's why from our assessment, up to 77% of the roads are unsafe right now for motorcycles. Same situation for pedestrians and bicyclists. Well, 80% for pedestrians and 91% for bicycles are still unsafe to travel on our roads here. Well, why I have to show this? Because this is the evidence showing that there must be something that we have to do. This is the evidence that we found from the road assessment. Pretending that you are a patient going for a doctor, the doctor cannot prescribe you any medicines without knowing why you are sick first. This is the symptoms. We know already what really happened. So the solution is to provide a suitable and appropriate countermeasures, how to get rid of these black and red areas. We want to achieve the World Health Organization road safety targets. 75% of the existing roads, 75% of the travel being on 3-star or better. So we have to somehow reduce the area for 1 star or 2 star for all load users. So that's something that we have to keep in mind. Comparing Thailand to the worldwide data, well, for the worldwide data, that's on the left-hand side, Thailand on the right-hand side. You can see here that if we look at simply the summation of the black one and the red one, that's unsafe situation, 1 star, black one, 2 star, the red one. Every bar in Thailand is higher than the world average. You can see here. That's why we have such an outcome in the sense that we have a lot of fatalities that I showed earlier. Every year we have almost 20,000 people died on our road. So something about the road infrastructure, we can blame it, in addition to the vehicles and road users. Now, let me quickly move to another part. That's the AI RAP and the potential applications for Thai roads. Before going in more details, let me briefly show you the attributes or the variables that we need to use in order to assess to get the star rating. There are a lot, more than 80 attributes here. Imagine that you have to do this coding for every road in order to find out how many stars your road has. It's very time consuming and it's very tedious. In addition to that, you have to get to know all of these attributes and how to do the coding consistently with the standards and specifications. Here, the problem is for one road section, we have to perform the load assessment here every 100 meter. So every 100 meter, you have to assess 4 load user types. 1 kilometer of road section, you have to do it 10 times already. What about, we would like to know the overall road network in Thailand or in one certain country. Well, that would take a lot of time and effort in order to, do all of these codings in order to come up with the star rating attributes. So that's the problem. Is it possible that we use some AI or some data that we can get it easily instead of, manually coding the data one by one? So that's our problem. You can see here from 2015 to 2022, the number of the road kilometers that have been assessed under the star rating. VIDA is the tool we use for the star rating assessment. We now are about just 5 million kilometers worldwide. But can you imagine how many kilometers of the roadways worldwide in every country? That's probably more than 100 million kilometers. Is it possible to reach that? Is it possible to assess all the roads? Manually, it's very challenging. But with the information technology, with the artificial intelligence, that could be possible. So from the previous slide here, we have to pinpoint which variables can be done automatically using AI, which variables are really important and affect the star rating. So that's something we can do to facilitate the process of the data codings and data analysis in order to come up with the star ratings. So that's why the International Road Assessment Program come up with what we call IRAP, AI RAP. It's actually stand for Accelerated and Intelligent. AI, that's for accelerated and intelligent. So we would like to improve the access to and the application of the existing and emerging data sources globally. When we mention about the data sources, it might be coming from advanced technology, from like tools like artificial intelligence, the machine learning, vision system, from LiDAR, from telematics, and from other data sources. Right, an example on the right-hand side here. There are many things that we like to have in order to assess the highway for star rating. Well, we need the speed data, we need the travel data, ADT, the average daily traffic data, we need the load geometry data, and so on. So we could use some of these technologies in order to help facilitate the data collection. So that's why the AI lab project gets started worldwide. As one of the example, this is from the Australian initiatives. They have what they call the AI lab automation for Australian road safety. So it's being done by many organizations, as you see from the right-hand side, with the support from the IRAP. So they are able to, deliver up to 20,000 kilometers of the attribute data automatically, extract the data automatically. They could help facilitate in the data collection for the iLab data coding attributes. For Thailand, we also have what we call the light star ratings. It's being used by the Department of Rural Roads. We try to minimize the time and minimize the data needed in order to come up with the stars. So the Department of Rural Roads come up with a process called the light star ratings, using less number of variables that come up with more or less the same quality of the star rating with the full model. So actually, this is incorporated as one tool, and they call it the Road Safety Audit System, or RSAS, under the Department of Rural Roads. And they just got the award by the IRF in 2021. They used some of the vehicle inspection data along with the cameras and sensors and so on under the DRR initiatives. And this is the software that you can measure the distance. You can look at the data like Google Street View, but this is their own software. Well, let me show you another example before I end this presentation. I would like to highlight target 4. Target 4, as I said earlier, by the end of the decade, we would need to have more than 75% of the travel on a safe road or 3-star or better. The problem is we don't really know where the 75% of the travel are at this moment. How to know? How can we know that where the 75% of the travel is? Let's focus on Thailand, for example. We need to establish the baseline data first. We don't know anything. We are working from scratch here. So we kind of integrate the big data from several sources. On the left-hand side, there are many road network and inventory data from several road agencies. On the right-hand side, also our crash data is really challenging. We got a lot of sources of the road accidents data, and we also incorporate the TomTom traffic data. So we put all together and work with the map, and finally we come up where the 75% of the travels are in Thai roads. So actually, out of 700,000 kilometers, we just need to focus on just 19,000 kilometers. So this is where we need to focus doing the road assessment. So if we can improve whatever we are seeing here to make it 3-star or better, we are good to go. So we can achieve the UN or WHO road safety targets easily. So that's something we have been working on. And we can look into details on who are responsible, like the Department of Highway is responsible for 86% of the total amount. The Department of Rural Roads, the Expressway, and the local roads, and so on. We also work on this at the provincial level. So let's say, for example, here, the Rayong province, this is the province with the highest road fatalities in Thailand. And we have already identified where the 75% of the travel are along with the risk map. And then we can look further on the details. So people under the road agencies can now know what part of the road network can be off focus and make them 3-star or better. So I think I'm running out of time. Let me end my presentation with this slide. So you can see that in order to achieve whatever we have discussed here, the input is very important. So we are talking about the multi-source data. We have the data coming from several sources. The accuracy of the data is also important, how to collect the data, how to set up the baseline data. And of course, people, the local capacity building, they are all important. So I hope that if we can somehow incorporate the AI here, that will help, shaping a good input here. And of course, if we have the process, good process, and we will definitely have a good output, and we will have our safer load condition, because as we always say, every life counts, not only in Thailand, but in every country. Thank you very much. That's all my presentation.
Thank you very much, Professor Kasem ค่ะ The next will be Associate Professor Mongkol.
Is there anyone who would have any questions?
Then shall we start? And hello and good afternoon. Then my name is Dr. Mongkol Ekpanyapong. Then my background is a little bit different. I'm a computer engineer. And then today I will talk about the AI technology for the road safety and maybe other applications. Before we start, then a little bit about me. Then currently I'm serving as the director of AI Center at the Asian Institute of Technology. Before I joined AAT, I'm a senior computer architect at the Intel Corporations. And then I joined AAT in 2009. And then I also helped co-found the AI Center and Pineapple Vision System, which is the AI startup company. I also serving as the president of the Intelligence CCTV Association Thailand. Then before we go into the road safety, then a little bit background about the AI. Then AI is coined, the AI term is coined since 1956. Right? And then it has been developed for quite some time before it getting as good performance as today. In 1959, then the term machine learning is introduced. The concept of machine learning is to give a lot of data to the machines so that it can learn from the data. And then 1997, we have the first time that the computer or the machine beat the world chess champion. In 2007, we have the DARPA Urban Challenge. And then 2011, we have Siri that can do the speech recognition. In 2011, we have the IBM Watson that win over Jeopardy game show. And then 2017, we have the AlphaGo that can beat the Go champion. That is the first. The Go is the game that people think that it will take machine very long time because it have many possibility to play the game, but it eventually the machine could beat the human champion. And in last year we have ChatGPT that I think everyone is aware of. Right? Then in terms of technology, then the last decade for the computer vision problem, it is considered be solved by the AI. Then now it have the capability that is as good as human or even better. Right? Then in terms of AI algorithms, right, it could be classified into 3 types. The first one is the rule-based. When we specify what is the algorithm that the computer should use. And then for the second generation, we have the simple machine learning. When we give the data, and then we have algorithm like decision tree support vector machine to be able to classify those data automatically. And then from last decade, we have the deep learning when it requires a lot of data, but as a result, it also provides a lot of performance. Also, with a lot of data, we also need a lot of computing power. Then these are one of the drawbacks of the deep learning technology. Then in terms of AI for road safety, for transportation, then we have in the early day, we use the AI for traffic information, like to collect the vehicle data. Then in the past, we use some other sensors like the magnetic loop, the RFID, the GPS to help, right? But as a human, we can just look and see identify whether this is the vehicle and what type vehicle it is. And then for the early day, for the traffic information, usually we also use the camera to detect the license plate information. Right? And then we also, at AT, we have some work that use the AI to do some helmet wearing or helmet not wearing survey. We also convert the vehicle information into what we call near real-time emission inventory, so that we can calculate what is the amount of PM 2.5 generated. Last couple of years, Thailand have a lot of these problems. In terms of law enforcement, then we use AI. In the past, it's similar. For law enforcement system, they use laser, radar or LiDAR to help detect the law enforcement violation vehicle. But with the advance of AI technology, then we could use the just camera to do the same task. We also have some work with the Dr. Garavig from the transportation engineering on the point-to-point speeding traffic violation. We also have some work that work with the Don Mueang Tollway to use the camera to detect anomaly on the road, like some object falling on the road. And then we also have another work that detect motorcycle falling on the road. Then these are some examples of the video that try to make the CCTV smarter. Yeah. We also call it CCTV AI. Then, for example, this work is the work that we work together with Chulalongkorn University on the Lama 4 model. Then we use the existing camera, and then we could count vehicle type, and then the number of vehicle as well as the vehicle speed. Then we could make it better than just the human eye. So in the case that we collect the speed information using just the camera. And then this one, we use the camera to count the queue length in meter. Right? For example, on the leftmost lane, right? The queue length is 50 meter and so on. And this one, it doesn't have any vehicle. Then we can tell what is the queue length for each lane separately. And then this one, we use the camera, the survey camera, to tell the turning ratio. We tell how many vehicles that turn left, and then this lane it will be go straight, and this one is to turn right. It we turn right to the expressway. And then we could count for vehicle type. We have the bicycle, bus, pickup, sedan, truck, van, and three-wheel vehicle, or in Thailand we call tuk-tuk. Then this one will be the traffic information that we get from the system, including the vehicle count, vehicle type classification, queue length, and turning ratio. This one is the mini camera that we install on the Lama 4 roads. Then this one is the technology I mentioned. And for the license plate recognition, then in the early day, the AI system is used on this technology to read the license plate, either to coming to the some gate or on for the surveillance applications. Then I'm not sure, but then it's quite small. I'll show you. Yeah, then this one you will see the license plate reading information. And then we also have the mobile application. Then in this work, we work with the traffic police so that they could, when they set up the police station, then they could check whether for this vehicle it is on the blacklist or not by using their mobile phone. Then if it's on the blacklist, then the system will alert. And this one, the system, the vehicle is not on the blacklist. And for example, this case, if it's on the blacklist, then the system will alert. Then it could help for the traffic police. And then this one is show that it's on the blacklist. We also work with the stolen vehicle police to help do the same thing, but install the camera on the police vehicle so that they could drive around the city and then use camera that install on the police vehicle to detect any blacklist, any stolen vehicle. Then like that mentioned earlier, one problem for the road safety in Thailand is on the motorcycle. And then this one is the data from 2012, when the 65% of the road accident fatality rate is come from motorcycle. And then this one we work with the ThaiRAP Foundation to collect the statistic of the no helmet wearing motorcycle, and then the helmet wearing motorcycle. We also differentiate between the adult or kid. as shown here, and whether it is the rider or passenger. Then this one, we use the existing camera from BMA to collect this statistic. And then this one is, oh, sorry. This one is the similar work, but we install the camera on the, just some temporary camera on the road to collect this helmet information. Without the helmet, then there is no counting. Once there are motorcycle come to the scene, then it collect the information and update the statistic, and then we plot this into the, we send this data to the website. Then usually every year, the ThaiRAP Foundation, they have to survey the number of, for all the provinces in Thailand, right? And then this system will help them to reduce the number of manpower. And then, oh, sorry. Then, as I mentioned earlier, in Thailand, we have the problem about the pollution, especially in the January or February. Then there are three main sources of the pollution. The first one is the open burning. Second one is the road traffic. And then the third one is from the industry. And also a little bit that contribute from the construction site. We try to build what we call the near real-time emission inventory model, so that we could know what is the source of the pollution, where they come from. And we also use the WAP-CHEM model, the WIF model, to predict whether for those pollution 5 days from now, where will it go. In terms of transportation, we collect this one. The number is the amount of PM 2.5. It show in the unit in gram per kilometer of the vehicle when they're moving. Then we convert our traffic information we got early and using some knowledge with the environmental engineering to build this system. And then we also have some work with the traffic law enforcement. Then this one, we work with the police in Phuket to do the red light traffic violation detection. We use only camera, as I mentioned earlier. Then the camera will detect the traffic light region automatically, and then we specify the area that we want to check, and then the area that the area before the junction and the area after the junction. Once the violation is detected, and we collect the image before the violation and then image after the violation, including the license plate information and the video of the violation. And then we prepare the ticketing system. We prepare the data for ticketing system so that the police could use to issue the ticket. Then this one is the installation site. We install in the 9 junction in Phuket areas. Then this one show the system that we use. Then it have cameras, and then we also install the radar to detect the vehicle speed, because from the police requirement to issue the ticket for speeding violation, you need either laser or radar. Then these are some deployed sites that we already deployed the red light violation system, including Phuket, Lopburi, Chha Cheong Sao, Nakhon Sawan, and Udon Thani. Then this one also used the AI technology to detect the lane change violation. Then if there is a vehicle that crossed the line here, then the system will do the automatically detection and then send this data to the traffic police. This problem, it could cause the accident, traffic congestion, and then it violates traffic law. This shows the example of the system in the Hue Quang area in Bangkok. Then we define the processing region. Then once the vehicle cross this region, then in this one we have the overview cameras, and then HD is the high definition camera to try to read the license plate on those areas. It like the traffic light system when we it like the red light system when we have to have multiple cameras. Then this one, the overview, we see the violation, and then we use the HD camera to zoom in to capture the license plate information. And we get the picture of the violations. Then these are the 15, oh, sorry. Okay. Then these are the 15 locations that the system installed in Bangkok area. And then this one, we also deploy the no helmet wearing violation detection system. This one we deploy it in Phuket and the Udon Thani province. Then if there are motorcyclists that do not wear the helmet come into the regions, the detection region, then the system will detect and alert automatically. Then we get the picture of the violation and then the license plate information. And then we send this data to the traffic police. This one, some 5 seconds video of the violations. And then this is another violation that we see often actually in Pathum Thani when we have the wrong way driving violations. And it's quite dangerous in Pathum Thani when you drive over there. Then this one we detect the wrong way driving, and then we collect the evidence and send this to the police. Then this one is the work that is done with the Dr. Kanavi. Then this one we use we call it point-to-point speeding violation. Then this one we install the system on the Don Mueang Tollway. Then in the past, the police have to use the laser gun to check the speed of the vehicle and then issue the ticket. Then we install the cameras into locations. on the Don Mueang Tollway. Then the distance is between is around 5 kilometers, different 5.5 kilometers. And then once the vehicle pass, let me check. Okay. Then once the vehicle pass the first location, we collect all the license plate information. And then once it passed the second location, we use timestamp, the difference between the timestamp to help calculate the vehicle speed, right? And then from that, we could check whether the vehicle is violate the speed on this 5.5 kilometer or not. And then this one is the work last year on with the Don Mueang Tollway. Then we install the system to detect anomaly on the tollway. They have about 159 cameras. And then if anomaly like this happen, and if it captured by those cameras, the system will detect or alert automatically. Then we use the AI system with the deep learning. Then in the anomaly, it includes the parking vehicle on the tollway, the wrong way driving, the falling objects, and then the human on the tollway. We also collect the statistic information like the vehicle speed, vehicle type, number of vehicle, and use that to update on the map on the control room of the Don Mueang Tollway. Then this one is the control room. Then the green region meaning that the vehicle speed is quite good, right? Then otherwise we can change to orange color and then red color. Then the blue dot on the map is the where the camera is installed. Then if the anomaly is detected, then it alert as shown in the video wall. And then the security guard could dispatch the rescue team to help for those who have the problem on their vehicle or to collect the falling objects. And then during the testing time, they test the Don Mueang Tollway test during the raining time, during raining at night time, raining at daytime, and so on to check the accuracy of the system. Then this one is the actual scenario when there is a bus that have some problem on their engine, right? And then the system could detect automatically. This one is the wrong way driving, but it's by the DMT vehicle themselves. And then this one is also detected the human on the tollway. And then this one is the police motorcycle. Then it also detected. Then this one, it detect the falling object, but it set up scenario when the Don Mueang Tollway people go and open the umbrella. And then this one, the system is tested by the company in Japan. Okay. Then this one, we also install similar system, but this one is on the Chanchuli Tower. Then if there is this one is for the Ramapho project. If there is any accident or any stop vehicle on the Thai-Japan bridge, right, then the system will alert to the officer. Then in this scenario, in the real scenario, that system could detect automatically. Then there is this vehicle come and stop in the middle at the middle of the road. And then these are some example of images that we could capture from the Thai-Japanese road, Thai-Japanese bridge. And then this one is to detect the motorcycle accident, right, using the AI. And this is the actual scenario. Then in our team, then currently I'm serving as the director. We have Professor Matthew Daly and the consult, and then we need a lot of AI machines to be able to do all this. And then the right hand side is the team. And thank you very much.
Thank you both Dr. Kasem and Dr. Mongkol for interesting presentations. So is there anyone in this room having any questions? Right, so there is a questions from Q&A here for Dr. Mongkol. The question is, what is the accuracy of real-time AI estimations for emissions? And could you explain a bit more about the development of technology behind it?
Then the first question is on the emission inventory,
right? For the emissions.
Then currently the accuracy is around 90%. And then the second question is the development of
the development of the technology behind
the
it,
the
emission as well. Right.
Then the emission inventory, there are two parts, the AI part that collect the traffic information, and then the second one that we have to convert it to the pollution information. Then we work on the first part when we use the traffic information, like vehicle count, the vehicle speed, and vehicle type. And from that, we can estimate the amount of pollution that it could generate from that vehicle, from that kilometer that we see in the scene. After that, then there will be the EEM engineer, environment engineer, that could convert this data into the pollution number and then give us the equations.
Thank you for your answers. So is there anyone in the online having any questions for both Dr. Kasem or Dr. Mongkol?
Hi, this is Dr. James Haworth. Do you mind if I ask a quick question? Can you hear me okay?
Yes.
Yeah, so thank you for the really interesting talk. You've done some really great stuff and it's nice to hear about all of that. I was wondering, so in the past year, there's been quite a lot of advances in AI models, which I think everybody's familiar with. So my question is, what do you think are the opportunities with new AI methods such as large language models and foundational models in this domain?
Then I think in the near future, we could use LLM to help identify those and then alert to the officer automatically, right? As per the last video that I sent, right? Then currently we still have to train a lot of data, right? But with LLM or something similar, I think it could help reduce those label data, those ground truth making time, so on. Yes.
Thank you.
Thank you. I think it's the time for the break, and we will see you in around 10 to 15 minutes. Thank you.
Hello.
Hello.
May I introduce Professor Nicola Christie? She's a professor in transport safety at UCL. Professor Nicola, take it away.
Okay. Thank you, everyone. Good afternoon in Thailand and good morning in the UK. Cycling in the UK has become a very political issue. It's seen as something that can help reduce emissions if people switch to cycling and improve people's health, because there is an obesity epidemic within the UK at the moment. So it's very much supported by politicians that want to make cycling-friendly cities. But of course, they are a very vulnerable mode. They can go onto the road with no training, no insurance, they're not licensed, so they don't have any license plates that we can use automatic number plate recognition with or anything like that. So data is really important about the incidents which cyclists get involved in. I have been in road safety for over 35 years, and the mantra about injury prevention is that it all starts with good data. So why is it difficult to understand risk factors with regard to pedal cyclists? Well, they're relatively infrequent events. Many can involve what I've called solo crashes. So they can become, they can hit a stationary object. They can, become destabilized because of potholes in the road or because there's insufficient light conditions. And even riding over engineering measures that are designed to improve safety, such as speed humps, can destabilize them. And there's also a question of underreporting. So if a cyclist has a crash on the road without involving anyone, then it doesn't meet the definition of an accident or a collision, which is being involved with a motorised vehicle. But we know that looking at hospital episode data and for cyclists that have been admitted, so this is a serious event, a serious injury, only 2/3 of these will actually appear in the National Police database. So we know that there's underreporting. So there's a kind of lack of data, which is not helped also by these individual crashes which happen, which don't involve anybody. And it was very interesting listening to the ThaiRAP. I'm very familiar with the ThaiRAP programme. And yes, we do want a world free of high-risk roads. And we know that things like the fatal collisions are the ones that are only the tip of the iceberg. And that for every fatal is what they call a whole hidden reality of things like amputations, quadriplegia, paraplegia, brain injury, where there is actually no end point for these people, and these disabilities carry on throughout life. So these are a huge burden to individuals and society. So fatals are one thing, but there are many other incidents that happen after this, and we need more data on them. So hearing some of the horrendous numbers in Thailand of fatalities, these may look very small figures to you. But for example, in Great Britain in 2021, there were 111 pedal cyclists were killed, and 4,000 reported to be seriously injured. And again, as I say, seriously injured could be head injury, it could be amputation, and life-changing injury, which, as I said, has no endpoint. Another part of my research is looking at the consequences of these injuries for people, and we know that they continue throughout life and affect people's well-being. So in London, only 7 people, I say only 7 people killed, and over nearly 4,000 people were in the bracket called killed and seriously injured. But we also know during this time that, especially during the pandemic, that cycling journeys increased hugely. And I was very interested to hear from the previous presentations by Dr. Kasem and Mongkol, that getting that exposure data and how many people are actually out there doing things is a very expensive part of kind of survey work. And if we can automate that, that's really, really important. So we need to know, we need to contextualize these injuries amongst how many people are doing this activity. And if many, many more people are doing it, and it may look like there's an increase in casualties, but actually it's become safer. I hope everyone can hear me. Okay, good. So, oops, sorry. So I was involved to actually get data on something that's a relatively infrequent occurrence is quite difficult. So I was involved in a piece of work that looked at historical data over several years in order to understand these risk factors in depth. So we looked at police fatal files. So these are in-depth investigation where they'll look at the behaviour of the cyclist. Was there any CCTV surveillance available for where the collision happened? And this is based in London. Understanding the collision partners. So what was their behaviours? If they were lorry drivers, where are they been delivering? At what stage in their delivery shift were they? To get the full kind of understanding of this. So these are the very infrequent events. So these are fatalities are just the tip of the injury iceberg. And what we did, so for every fatal file, and we had to go through a huge amount of ethical procedures to be able to access these. We supported it also with looking at the Google Street View of the location to see what the location was like and what countermeasures had been put in as a result. So this is 5 years of data that yielded 79 fatal and life-threatening collisions. There was only 1 or 2 life-threatening collisions involving cyclists. So this is where people had lost limbs. But there were only 53 available for analysis. And the reason for this is that if there is an ongoing legal proceedings, then we're not allowed to look at the cases because they're not complete cases. And this is something that will probably happen in any country. When we looked at the data, heavy goods vehicles or heavy trucks was a collision partner for nearly half of the crashes. Now, anyone who has travelled to London will realise that London is a very large construction site at the moment. There are huge levels of construction. So we are in a situation where there are many vulnerable road users interacting with huge, massive trucks. And the majority of these crashes involved left-turning vehicles. So where the truck was turning left across the path of the cyclist. And ironically, females the proportion of females of the people who cycle in London is around 25–35%. But females were really overrepresented in these collisions, much more than males. So what is going on in this situation? So there are female cyclists who are positioning themselves in such a way that the lorries could not see them. And they were being destabilized by the front wheels, and then the back wheels would run over them, causing catastrophic thoracic injuries. So a cycle helmet would not make any difference to these kind of injuries. One of our own lecturers, who is a climate scientist, she was killed in exactly this kind of scenario. So it's a real thing that affects everyone. So as a result of this work, so this work was commissioned by Transport for London to inform their cycling action plan. And one thing I'm really keen in this presentation is to show how data can be used to influence policy and then be used again to evaluate what happens as a result of interventions. So in London at the moment, they're working towards what's called direct vision, so that any truck driver in their cab will be able to see to the side of them with any kind of, whether it's using cameras or whether it's having a largely glass cab. And London is working towards this standard to protect cyclists, because they know this from this research that this is problematic for cyclists. They also have done a huge amount of behaviour awareness programs. So we could see that when we looked at these fatal files, so there was one cyclist who was actually in front of one of these lorry cabs. And if they're in that first metre in front of a cab, the cab driver cannot, the lorry driver cannot see that cyclist. And they were destabilised and killed from a rear end crash. But many of these, as you can see, this is kind of a left turning lorry. And if you've got cyclists there and you have the right equipment, you will be able to see them. So this is a way of showing how our research, looking at that in-depth, infrequent data over a long period of time, has managed to inform these kind of interventions. And again, it shows the importance of curb separated cycle lanes to make sure that if you've got all this complex mix of traffic, these massive, physically massive vehicles alongside these very vulnerable road users, then we need to kind of segregate to ensure that they're safe. Now, in terms of understanding, this is an example from occupational safety, which shows the kind of relationship between one death and how many more serious accidents, minor accidents, and near misses and unsafe acts. And you can see that the near misses and the unsafe acts are the more numerous types of data. And that is the kind of data that we can focus on. And we know that they resemble actual collisions. So taking that in mind, that we can kind of work on understanding these more numerous data to kind of inform our understanding of risk factors. So as I said, so ideally with some kind of AI, we can actually start to predict actual collisions from understanding near-miss data. And this is a project that James will talk about a little bit later. And you need to conceptualize safety events within a safe system. I'm sure many of the Thai participants will understand the safe system. So this is really about safe roads, safe speeds, safe road users, safe vehicles, and post-crash care, so that there is an emergent response that can get to those people very quickly. And so we need to understand all aspects of these kind of factors, and we need to understand safety culture. Now, safety culture is very close to my heart because I do a lot of work on occupational road safety. This is called the Safety Culture Ladder, which was done by Patrick Hudson, who is mainly working in like the high-risk industries in oil and gas. And it really describes, how we can use data. So it starts with what's called a pathological approach. So who cares as long as we are not caught? And I would say that my work looking at motorcyclists in the gig economy in the UK and the tech companies that support that kind of work is pathological. They don't care about people's safety. They produce work that's highly pressurized, with no safety training, and people just go there and do the work, and we know that they report more risk than an ordinary cyclist. And I would describe the next level up is reactive. So in Great Britain, we have largely had for many years a reactive approach. So safety is important. We do a lot of it every time we have an accident. And we are moving more and more towards what's called calculative and proactive, so that the road danger kind of movement in the UK saying, look, there are dangers on the road. If we address those dangers, then we can prevent collisions happening, rather than waiting for something like, you know, I heard the expression hotspot being used quite a lot in the presentation. So that is reacting to something that has happened, and it is much better to prevent something from happening rather than reacting to its effect. So this is where AI in particular can help us predict and understand casualties. And if you think of the aviation industry, where you wouldn't let too many planes fall out of the sky before you decided to do something, it's very generative. It's, you know, this is the absolute core function of their business. So I think there is a lot of work to move to being more proactive in road safety in many countries, rather than just looking at what's happened, actually being able to predict. And this is where AI, I think, has a massive role to play. And when we are designing interventions, we really need to think about modifiable risk factors. So we can't change someone's age or their gender to change their experience of being a road user. But we can look at their behaviour. We can look at the environment. I come from a background in psychology, and I know one of the most powerful ways to change behaviour is to change the environment in which people act. We can also look at how the system is managed and looking at compliance and enforcement, and look at laws and regulation. But laws and regulations are really a long-term kind of solution, but all these other things we can change in the short and medium term. So we really need to think about interventions, understanding the data, what it tells us about what's happening, and being able to frame our interventions in this way. So I'm always very keen that any kind of intervention is evaluated, and there's a continual cycle of feedback. In the UK, we have something called the Green Book. So this is about appraisal and evaluation in government, and guidance on what to consider when designing an evaluation. And this is called the ROMEF cycle. So, you know, what's the rationale, what are the objectives, how do we appraise it, monitoring, evaluation and feedback. And I think from the first two presentations, you can see how collecting that data around, you know, just the traffic use and getting data on levels of traffic, who's using what, is really, really important. But actually with pedal cyclists, and understanding the individual behaviour and understanding who is doing what and where, we don't have a number plate that we can link that person to a whole set of data. We have just a road user, so it's really important that we get that information. So anything that can assist this cycle of evaluation is very important. So I've been working with James Ekpanyapong and some other of his PhD students in developing a policy tool to use near-miss data in intervention design and evaluation. Because cycling collisions are so infrequent, we just don't have the numbers of collisions in order to evaluate interventions. So this is why these kind of tools are very important. And we know that most intervention approaches need to be multidimensional and multi-agency. And multidimensional, I mean, in terms of a safe system, we need to talk to car drivers, we need to talk to cyclists, we need to change the environment, we need to work with the police, we need to work with road safety officers. So there is a whole, all the research says that doing it in this way is the best way to get the best outcome. And what I thought was quite interesting, so having that mobile near-miss reporting and computer vision analysis allows us to understand who is experiencing problems, where they're experiencing them, when and what behaviours were involved. And we can do this because it's mobile. We can often, like the CCTV cameras or the cameras that were described on the smart highways, described in previous presentations, are looking at the kind of strategic network. So if we have that camera on someone who is going up a quiet lane or on a cycle superhighway, we will know data about that individual. We will know where they're traveling. So we have the exposure data, so how long they're traveling for. We will have their speed. We will be able to look at their interaction with other road users, whether they're pedestrians or car car drivers or heavy goods vehicles. We can understand that interaction in a kind of holistic way. And I think that holistic systems approach is really critical in understanding any kind of risk. And we can identify what needs to be changed. So do motorists need to be giving more space to cyclists? So there has been a whole campaign around close passes in London. So if someone is travelling too close to a cyclist, giving them the right amount of space and making public awareness campaigns. And there's also been Operation Safeway, where the police have been looking at the behaviour of cyclists and of vehicle drivers and stopping them over and talking to them if they feel that they have been behaving in a way that causes risks. And lots of information around blind spots between trucks and cyclists. And then we can make these changes and use data to evaluate this using near-miss data. So this is the goal, that we can have a whole cohort of road users providing crowdsourced data. And ideally, and I totally understand where the other presentations are coming from, to have that real-time data and to have an e-call function if a cyclist is knocked down, to alert the emergency services. And the whole purpose of this would be to have a policy evaluation tool. So getting frequent data that we know resembles actual collisions. And do these actually go down? So if there's a massive investment in infrastructure in the city, if we look at near misses before that and during and after, and for some time after as well, to allow behaviour to bed in, do we see a change? Are near misses reduced? And can that support the safety of road users in the cities? Thank you.
Thank you very much, Professor Nicola. Anyone has a question here? I have a question. How is it difficult to change the law and regulation regarding road safety in the UK?
It takes a very long time because our current government doesn't see law or intervening in changing behaviour in that way as the right way to carry on. It takes a long time because you have to pass bills, they have to go and be assessed. So it can take 2 or 3 years to introduce law.
Very
So
much
people,
same
yeah,
situation.
and actually the answer may be to actually enforce the laws that we have rather than introduce new laws. And they're very, for example, they're very unlikely to introduce mandatory helmet wearing for cyclists because they are worried that it could make people decide not to cycle, and therefore all the health benefits that cycling brings will not be delivered.
Very much. James, do you have any question?
Hi, thanks for the talk, Nicola. It's very interesting. Obviously, I know it better than some other people. I wanted to ask, so a lot of your research is focused on the UK and London in particular, and some of the issues that come up may be quite specific, like the left-turning lorries and in particular female cyclists. So what do you think the issues are, or the challenges in translating this kind of research to other contexts, in mind of the fact that we've got a Thai UK conference?
Yes. Well, I think, looking at the previous presentations, I think that they're well ahead of the game. So I think translating it is about data, good quality data. I don't know how that is collated within a Thai context, but you really need excellent data in order to understand contributory factors to the collisions that have happened. And then collecting this other data where you can use AI to understand all the collisions, I think it's really, really important. So I think it's readily translatable to any country context. But understanding the demographics is really important. So, as I said, when you're using static cameras, you don't really know very much about the individuals. But if you're actually having a mobile sensing technology, then you can relate that behavior to an individual. And I think that's absolutely critical because, you know, is it older people, younger people? Is it people who've been trained, who've not been trained? And we are collecting all that data within our cycling project, so we will know, have they done any training, how experienced they are, how often they commute, have they had any previous collisions? So we have that, and we can linking that individual data to their behavior, to the road network. I think that's translatable anywhere we go. I don't see why not. But it's obviously, you know, you would need to get people to subscribe and be part of the study. But I think that'd be an excellent study to do in somewhere like Thailand, especially with motorcyclists. I mean, obviously you have a bit more data about them because you have their number plates, but we don't have that for pedal cyclists. So that's why we need individual data.
Thank you. Sorry, Garavig, I turned off the camera for the room. I don't know which one it is to turn it back on. Let me see. Maybe, oh yeah, there we are.
Yeah. Okay. The next speaker is Professor Bani. Bani, please.
Thank you very much. Thanks a lot for having us here. I start with sharing my slide, and please help me with indicating whether you can see this slide. Can you hear me well? Can you see this slide?
Yeah, we can see that and it sounds great. Thank you.
Yeah, great. Thank you very much. Thank you so much for the invitation. We are very happy to be here. And as mentioned earlier, I'm Bani Anvari, and I'm going to deliver this talk with my colleagues Milan Lovrik and Jan-Luca Kessel. And we are going to talk you through orchestrating safety and serenity with autonomous vehicles. Robotics and automation has been very well implemented in industry. So for instance, here you can see an example of car industry with Tesla, where the robots are assigned with predefined tasks, and they are working within a closed environmental, within a closed environment where humans are not allowed to enter their working space. And as soon as a human enters their workspace, they all need to be stopped so that the human can interfere. And then as soon as the human leaves their space, they will continue with the assigned tasks to them. This trend has moved to collaborative robots, and here you see an example from Choocharukul, where humans are safely working alongside robots. And for this type of robots, a new generation of robots or collaborative robots or co-robots have been generated, and the trend continues this way. Robotics and automation has been also supporting transport and mobility services, and many examples. I give a few examples here to you. For instance, the autopilot in commercial flights, which have been introduced from 1917. Most of you might not be aware, but when you are traveling from A to B using an airplane, at 90% of the times they make use of autopilot while getting you to your final destination. Another example is the automated metro industry, where there have been around since 1920s, and one of the examples is London's Victoria Line, which is the world's first newly built fully-scale automated railway. And this trend continues towards autonomous vehicles, where there have been experiments more than over 100 years around them. And now we are at the stage where different levels of autonomy are in place, and people agree basically on definitions of different levels of autonomy. So many of you might be familiar with this, but I quickly go over the definition from SAE, which talks about levels of autonomy ranging from 0 to 5, 0 being fully manual and 5 being fully automated, where you almost don't need the driver anymore in place. On our roads at the moment, we see commercial vehicles with autonomy level 2, up to autonomy level 2, where the driver still needs to be engaged in the driving task and observe the environment and monitor the system at all times. However, last year, Mercedes-Benz introduced the first internationally valid system, which is approved for conditionally automation or level 3 automation, basically. What is important here to note is that they highlighted that this type of vehicle is suitable for motorway sections where the traffic density is high. Basically, the vehicles are also not allowed to go more than 60 kilometers per hour on these motorway sections, and basically up to the legally permitted speed mentioned for this type of vehicles is 60 kilometers per hour. There have been many predictions regarding the regarding the revenues that these vehicles can produce. And I'm just bringing an example from a McKinsey & Company here, where they have said that advanced driver assistance systems and autonomous driving systems could create $300 to $400 billion in revenues by 2035. They basically said that autonomous driving could produce substantial value for drivers, for the auto industry, and for the society. So we are, within my team, we are interested in looking into integration of autonomous vehicles and systems into our society. So on one side, we look into integration of autonomous shuttles into our urban environment. And on the other side, we look into creating human-centric, intuitive interfaces for autonomous vehicles, where we are actually trying to help drivers with the task of handover when it comes to highly automated vehicles. For each trend of research that I am summarizing or I'm highlighting here, I will hand over to my colleagues to talk you through the studies that we are doing. But before going there, I just want to put this in context. When it comes to interaction, the interaction is a very complex thing, and its context varies from country to country, continent to continent. So here you have an example from Vietnam, where you see interaction with multiple different types of users: pedestrians, motorcycles, car drivers, van drivers, and so on. And if you talk to the local people, they tell you that for negotiation of right of way within this system, they actually should avoid any sort of eye contact with other road users. So pedestrians will avoid any sort of eye contact with the car drivers, otherwise they will not be able to cross the street. And this is, of course, very different from what we experience in Europe, as eye contact is a safety element. It's quite important for the safety of pedestrians, for instance, to have eye contact and make use of hand gesture to make sure that they can safely pass the street and communicate with, for instance, car drivers. To the level that the Driver and Vehicle Standard Agency in the UK also highlighted this, not only for pedestrians, but also for car drivers, that various elements such as hand gesture, as you can see in this video, and warning signals like flash headlights or sound horns are essential for assuring safety for all the road users. And also they highlighted cooperation of highlighted that cooperating when it comes to interaction with different users is of paramount importance when it comes to vulnerable road users such as cyclists, pedestrians, scooter riders, and so on. And this eye contact is so important that we have seen even some campaigns being in place to highlight this to people, especially to pedestrians, that you need to have you should keep having eye contact with, for instance, car drivers. So here you see the Department of Transport of Denver, where who have organized a campaign to do this activity. Talking about interactions with interaction of autonomous shuttles with vulnerable users, we have done some experiments in our laboratory at UCL Pearl, and we are going to talk you briefly over what we have been doing and what we are doing at the moment. And at this point, I would like to hand over to Milan.
Thank you, Bani. Good morning and good afternoon to attendees in Thailand. So I will be talking about the experiments we ran at one of our premier research facilities in London. And these are the experiments using an autonomous shuttle and human participants acting as other road users, which are often deemed as more vulnerable. So we are talking pedestrians, cyclists, and e-scooter riders. And we also had the participants sitting inside the shuttle during experiments. So we designed 3 separate experimental scenarios to study how different means of communication coming from the shuttle can be used to improve safety of interaction. So the first one was, Bani, can you please click on that? Thank you. So the first scenario was an e-scooter rider overtaking a slowly moving autonomous shuttle. The second one was a cyclist doing a right turn at this intersection in front of the incoming autonomous shuttle. And the last one was a pedestrian crossing the road in front of the shuttle. And the experimental design was very simple. So the next, please. It was a 4x2 factorial design. We had 4 means of communication and 2 environmental conditions. So we had nothing, meaning there was no communication from the shuttle. There was a visual communication by means of a laser projection. So we had the laser attached to the front of the shuttle, and it was projecting a red line onto the floor in front of the shuttle, indicating sort of a space in which the shuttle would brake intensely should something come in. We had the audio message playing from the speakers on the shuttle. So this was AI-generated male voice saying, "Mind the space" in front of the shuttle. And we had the combination of audio and visual. In terms of the environment, we had night and silence within the lab. And the other one was very bright daylight, plus traffic noise being played in the environment. So now I want to show you in the next slide a video recording of what one of these experimental runs looked like. So this was during the night. You can see the laser projection. I'm not sure if you will be able to hear the message, but it's saying "Mind the space" in front of the shuttle. As this e-scooter overtook, the shuttle slowed down, it was braking, and then it continued its journey. So now I want to show you the same thing, but this is the first person view of the same e-scooter rider. This was recorded with eye tracking glasses. And what they also give you is this red point showing where what the person is focusing on. So hopefully you can see that this participant did notice the laser projection as they dwelled for a while on that point. So we had 8 experimental runs for each participant. And then we did short questionnaire, which we gave to the active participant, in this case, the e-scooter rider. And we also gave questionnaire to 3 people sitting inside acting as onboard passengers. And the first question was, how safe did you feel during the interaction that you just experienced? So we are happy to see that our participants felt predominantly safe during these experiments. And there are some differences. So when nothing was used, there was no communication from the shuttle, it peaked around slightly safe for the e-scooter rider, but when something was used, either visual or audio, it became moderately safe, and with the combination, it was very safe. So this shows, if nothing else, the communication can improve the feeling of safety of road users and onboard passengers. On the next slide, I also looked at how this feeling of safety relates to the intensity of the braking that happened during the interaction. So we asked the passengers to rate their perception of braking intensity on a scale from 0 to 10. 0 meaning there was no braking, so the shuttle continued with the same speed, and 10 meaning it was an extreme level of braking. So obviously the shuttle would brake more intensely if the overtaking distance is lower. So this is kind of a more aggressive cutting in behavior. And then it makes sense that this type of interaction would be deemed as less safe, if not unsafe. And we can see when the braking was 0, 65 responses were very safe, and then the percentage of very safe drops to 15% when this braking was more intense. So on the next slide, we have the last question in this short questionnaire. We asked them how useful was each means of communication employed in the experimental run. And I'm showing this separately for nighttime and for daytime with traffic noise, because there was a very strong moderating effect of the environment. During night, all means of communication are deemed to be useful, the combination particularly so. But when we move to daylight, the usefulness drops, especially for the laser. So many riders said that it was very useless, and this is unsurprising because the laser projection can only be seen clearly during night. And as the lighting increases, it gets washed out, and then it's almost invisible during daylight, at least for the output power of the laser that we could use safely in these experiments. So all in all, I think this questionnaire shows that these means they do make sense. They improve the feeling of safety. However, we are aware that these are just questionnaires, so there could be some response biases such as social desirability. So we wanted to make sure that we also are able to record, measure, describe, quantify the behavior of the participants, because ultimately it's behavior that determines the safety of interaction. So on the next slide, this is how we used recorded behavioral metrics. We had eye tracking glasses for every active participant, as I've shown you before. We had an EEG cap for the pedestrian to record brain activity. And finally, we had motion trackers, these small devices that we put, for example, on the back of the safety helmet. So this recorded the orientation of the head, the free acceleration of the scooter angular velocity. And we also put one of these devices inside the shuttle. So this gave us objective measure of the intensity of braking, which we can then compare with the subjective ones from the questionnaire. And last but not least, we had lots of overhead camera footages of all interactions for all three scenarios. So we intend to use AI to detect objects in the scene and then to quantify distances between active participants and the shuttle in the very moment of interaction. So for example, for the e-scooter scenario, we want to quantify the overtaking distance in front of the shuttle, as well as the lateral distance as they're approaching the shuttle. And this will answer one of the very important questions: did they or did they not change the behavior when there was communication from the shuttle, drawing attention to the space in front of the shuttle? So as soon as we know, we will make sure to disseminate these findings. Until then, thank you, and over to you, Bani.
You're muted, Bani.
Sorry, thank you very much, Milan. Now we are moving towards the second trend of research that we are looking into which is on intuitive human-machine interfaces for autonomous vehicles. And within this topic, we are going beyond visual and audio feedback, which you see in commercially available autonomous vehicles. We have developed a haptic driver's seat, which Gianluca is going to talk you through, and I will hand over to Gianluca at this point.
Hi all, thanks that we can be here. Right, so we've heard just now that we now have first vehicles in autonomy level 3. So basically cars where you can hand over control to the car and you don't have to monitor the road around you at all times anymore. But this is conditional automation. So at one point the car will ask you to take back control if you're the driver. And obviously, if that happens immediately, you have no idea what's going on around you. And that is then a very unsafe transfer, because imagine you drive on a highway, even if it's only 60 kilometers per hour, there's a lot going on around you. This driving task is, after all, a very dynamic task. So we're looking here in how can we make this transfer of control from car to driver more safe. And one of the main ideas here is that we measure eye and brain activity of the driver in a driving simulator, and then employ artificial intelligence and machine learning to understand at any given point how much situational awareness, so to say, how much knowledge about the environment they have, and then give them appropriate feedback early enough so that they can take over the driving task in a safe manner. This is pretty much backed by research. If we go to the next slide, because...
Sorry, I don't know, for some reason, my next slide clicking doesn't...
Ah, there we go.
Yeah.
Amazing, no worries. So there's this piece of research here. For example, just as one example, that Tesla drivers become inattentive when the autopilot is activated. And obviously in a Tesla, that is quite tricky because a Tesla is not a level 3 car, but a level 2. So there the driver has to monitor the road at all times. And this inadvertently leads to accidents, to fatal crashes as well. Here an example from 2018, so a couple of years ago, but this is very much ongoing. And as part of this research, we're also looking at crash reports from different national entities. Currently, there are more than 30 crashes being investigated that might involve the autopilot. This is a current figure, out of which about 50% had a fatal outcome. So this is very much an important field. And the question here is, how can we effectively communicate with the driver? So in 1956, GM had this futuristic vision, let's say, of some sort of road traffic control, just as we see it in air traffic, where we have air traffic control, where basically you switch to another lane and then you do some fancy stuff on your screen while someone talks you through that, and then you're suddenly in autopilot. Yeah, obviously with the amount of cars nowadays, we didn't go this way. Yeah, and there is no road traffic control where a controller would talk to you at every given point. So we're very much dependent on vehicle to user or vehicle to driver communication. And state of the art, as most of you might know, is visual and audio feedback. So visual means there's some sort of like little icon on the dashboard, or maybe a bit removed, something bigger, some red screen popping up to tell you, please take over now. Audio is that you hear a beep sound of some sorts that gets more and more alerting over time if you don't take back control. But now that you're actually allowed to engage in other tasks, so let's say you're allowed to watch a movie or something, you might not catch these. And this is exactly what these fatal crashes also show. So we thought, why not building haptic feedback? So basically giving you feedback through a completely other different sense. And then the only real connection you still have to the car is the driver's seat. So here you can see we have built soft robots, so to say little air cushions underneath the leather of a real driver's seat that then inflate and deflate to give you this mechanotactile sensing touch. And this research very much has been published already. It has won several prizes as well in national and international competitions, for example, by Ocado and the BMW group. So this is our facility in East London at UCL Pearl, where all of this comes together. So we have a real size car simulator here. It's a real car with a screen around that is plugged into our in-house developed simulation environment. And of course, we have audio and visual feedback there, but we also have the driver's seat in the car. So it's very immersive. The participants can't really see the edges, so they really think that they're sitting in a real car, which gives us just this hunch of reality, really, when we do our experiments. So in a first step, we looked at how well the seat is received. And this is on the next slide as well. Yeah, so how well the seat is received. How is the acceptance? So to say usefulness and satisfaction. How do people perceive it? What is the intuitive feeling? Intuition is very big in driving, like intuition and experience. And how user-friendly and how effective is the feedback we give. And what we found is that, well, for all these questions, useful, good, efficient, assisting, raising alertness, or pleasant, nice, likable, and desirable, if we ask the participant before they actually tried the seat, what do you think? It already scored quite well. But after they actually then used it, this is the light blue scale, it got even better. So basically, people very much liked the feeling, and really in every of these categories, usefulness and satisfaction categories, there was really high acceptance. And we then also compared it to results we had from a visual takeover system from a BMW 5 Series car. So very much something that is already in use. And our both usefulness and satisfaction almost all the time scored higher, well, both for usefulness and satisfaction. Yeah. So with these results, we then went one step further and we said, now, how can we understand how much situational awareness these people get, and can we get successful transfer of controls by giving the people haptic feedback on top of audio and visual feedback? And for this, we designed a highway scenarios. The car is driving on the motorway. And at one point, well, the driver, the participant who's sitting in the car, is reading a magazine the whole time. So they're basically very much removed from the driving task. And after a randomly set time between 150 and 240 seconds, they are alerted by the car through visual, audio, and haptic feedback, or, well, either one of them or a combination of these, and they have to react to a situation in front of them. So basically there's a car, a stationary car sitting in the same lane, 7 seconds ahead in front of them. And if they don't react within 7 seconds, they will crash into the back of the car. And we looked at different things, mainly to understand, do they react quick enough, but also is there enough safety involved? Yeah. And we can very much see, if we look at the reaction time distribution of visual and audio feedback, that's the box plot on the bottom right, then we can see that people more or less took a bit more than 5 seconds in mean to take over and do a maneuver to avoid the car in front. So basically it took them 5 seconds to look up, to orientate themselves, to regain their knowledge about the environment, their situational awareness, and then do the maneuver. But if we put haptic feedback in the mix, so visual, audio, and haptic feedback, then this dropped quite extensively, yeah, which means people respond faster and manage to understand their surroundings faster if they get this extra sense of touch feedback. And this also shows the safety factor on the right-hand side. Higher safety factor means there is, it was more timely, so it was lower reaction times, and it resulted in more successful transfers of control that we would rate as this was safe. So basically they checked their mirrors, they did no abrupt maneuvers, no harsh braking, and so on. And you can see that by far the highest score is actually reached for visual and audio and haptic feedback. So again, putting this haptic feedback in the mix. And yeah, so this really shows us that haptic feedback might be a very good addition to the current audio and visual feedback that we get in cars to then allow for this autonomous driving, but in a safe manner that we hopefully can avoid the crashes we've seen in the start. And with that, back to you, Bani.
Thank you so much. Thanks a lot. And of course, these are some of the challenges that we are looking into, and there are many more challenges that within this field we are facing, such as issues of communication networks, vehicle to everything based communication, investments into the infrastructure, and also understanding complex social interaction, as well as management of edge cases where we have not specifically trained our systems for. They are rare, so it's difficult to collect data for those ones, but at the same time, they're very difficult to predict. And of course, as most of you know, regularity challenges that we are facing for introducing these technologies to our systems, integrating them, and making use of them in a safe manner. Thank you so much for your time, and we are very happy to take your questions.
Right. So is there anyone in this room having any questions?
Could I ask a question, please? It's Nicola here.
Sure.
How did you compute the safety factor?
So the safety factor is really just the ratio of successful transfers of control over all transfers. So some of them resulted in a crash. So we looked at how many percent were a successful transfer of control, and we divided that by the mean reaction time. So basically lower reaction time has a higher safety factor, and more successful transfers of control result in a higher safety factor. It's just really to combine several different metrics into one.
Yeah, and with your participants, did you manage to look at things like the impact of age on reaction time? I mean, reaction time is a very individual thing, I know, but I just wondered if you did that.
So in the results you see here, that was, or that is still a preliminary stage of the research. So they're not too many participants so far. I think in this one there are 10 or 15 included. So even if I would look at so I haven't looked at the impact of the age, but even if I would look at it again, I don't think there would be a lot of correlation just because there are not so many samples here. I had a whole range of people in between 20 and 64 years, and I can't quite make out, for example, a difference in how they react or how many safe transfers of control they have. And that's probably just because even if you might get a bit slower, especially when you reach, I don't know, 70, 80 years, you still have a lot more experience, and that makes up for a lot. Yeah.
And if I may add to this, one of the things that from initial stages of the research we were aware of was that if haptic feedback is a good sort of type of feedback to introduce in combination to the existing types of feedback, it still needs to be personalized for the driver. So the amount of basically pressure that you're introducing can vary from gender to age to season to type of car. So we were fully aware of this element when we started the research. The ones that we presented here, they're from 15 participants, but I believe, Gianluca, now we are having...
We're above 30. We have a lot more participants in, but that is still under investigation, under analysis for now.
So, and also to add, this is different from the first trend of research that we talked about, where we had in the first trend, we had a very good distribution of people and a very healthy number of people for making conclusions. Sorry.
Thank you.
Thank you very much for your question. Obviously, you all have our contacts. Happy to share the slides afterwards as well. If you have any questions later on, feel free to drop us an email, and we would be very happy to communicate or to talk to you via email or in another meeting that we can set based on your availability.
Thank you. I literally have a quick question for you as well. So, is there anything we should concern about if we, let's say, we wanted to implement this study in developing countries such as Thailand?
Do I have, sorry, what was the question? If it goes to developing countries, do I see any issue?
What should we concerned about? Like if we wanted to implement the study to in such a Thai context?
Well, it's a very good question, and maybe I refer to the fact that culture and the context, as I highlighted in my slides also, matters a lot on what needs to be introduced for successful interaction and cooperation between these systems and humans. And because of that reason, for instance, in the first trend of research that we were looking into integration of autonomous shuttles, into our urban environments, we were doing trials in multiple European countries because that can, the culture, the context, everything can have an impact on the results. So we haven't presented the results of that one. So definitely these things are important. I wouldn't say they're concerning, but definitely all these things doesn't fit all. So it needs to really be analyzed in its context. It needs to be reevaluated and utilized for the context that this is going to be applied and used for.
Thank you.
No worries.
Okay. Last but not least, we have Dr. James Haworth, who will give another last presentation. I will pass over to James.
Thank you, Nachapon. First of all, I want to say thank you, especially to Nachapon and Garavig and the local team for organising the event, taking care of everything in Thailand. That's saved me a lot of work, and I really appreciate the effort you've put into this event. And I also want to thank all the speakers for the great talks that we've seen so far, and all of the participants, both online and in person in the room, for joining today. We hope you found the event useful. So this talk I will share with Nachapon. I'm going to start by talking about the 100 cyclist study. So if I can just get control of my slides. So the general topic we're talking about is deep learning for road traffic safety analysis, which is something that we've been doing quite a lot of work on over the past couple of years. So I'll start by talking about the 100 Cyclists project, which Professor Nicola Christie alluded to earlier on. And then we'll switch over to Nachapon and he'll talk about some of the very early work we've been doing with some of the new large language models and foundational vision models. Okay, so the 100 Cyclists study. This is a project that's been going on for a number of years. It was disrupted by COVID, but we're finalizing the results now. So we've got the last few participants have been collecting data on the roads using GoPro Max 360 cameras, and we just got those back over the last couple of days. So full results hopefully will be out over the summer. But this talk is just trying to give you an idea of the role that deep learning plays in the research that we've been doing. So just a bit of background, and I think some of the other talks have alluded to this as well. So cycling in cities, cycling is prioritized by transport authorities because it's known to be a green transportation mode. Bikes take up less space than cars on the road. It reduces congestion, reduces environmental pollution, and it also has positive health outcomes for the individual. So there's obvious reasons why transport authorities would want to increase cycling as a transport mode, but in many places, not least London, but in particular, probably places like Bangkok, uptake is limited by the perception of cycling as a risky activity. And as Nicola talked about earlier, casualty data tends to be limited because of the low mode share, so it's difficult to quantify risk. And the point of our 100 Cyclist study was to collect data on near misses, which we define as a situation in which a person was required to act to avoid a crash, for example, braking, speeding, swerving, or stopping. And this is extended to include moments where the rider felt unstable or unsafe, such as close passes and tailgating. And close passes are known to be a problem in the UK. And if you're a kind of avid cyclist, you'll see lots of videos posted on YouTube and other sources of people being close passed on a daily basis. Okay, so linking up to Bani's talk, I want to mention a little bit about vulnerable road users in the age of, or the coming age of connected and autonomous vehicles. And Bani showed the image from the SAE of the levels of autonomy from 0 to 5. There's a really good review that came out quite recently in Transport Reviews by Kapasisis and colleagues on bicycle smart technology. So this also has 5 levels, starting with 0 at the bottom, which is basically your average person going out on their bike for a ride. Then we have things like passive assistance, which is, oops, where's my, yeah. So at the moment we have things like passive assistance. So certain computers, GPS devices will send a warning if you crash. They're able to pick up the movement from the sensors that you've crashed and send a warning to a contact. We also have navigation systems, so you might have mapping on your mobile phone. There's also increasingly warning systems being used. So, for example, there's a product called the Garmin radar, which will tell you of vehicles approaching behind when they're far enough away that you don't even know they're there. But that will pop up on your bike computer and tell you there's something approaching, which from anecdotal evidence seems to be very useful for safety. There are instances of things like cruise control on bikes and anti-lock braking systems, which qualify as active assistance. Those are kind of not really widespread at the moment, but they're becoming more used. And moving forwards, we're going to see things like B2X, so bike to everything communication, linking up with the types of connected and autonomous vehicles that that Bani was mentioning. And this all draws into the fact that in general, there's lots of R&D on connected and autonomous vehicles, primarily about making those vehicles safe and making sure they don't collide with other road users. But there's limited research on how those other road users, say pedestrians and cyclists, can make themselves safer in this new kind of age of automation that we're going to be seeing. Okay, so we're not quite there yet. Although there are some examples. So we have a PhD student working in roads where they have an e-scooter system where the speed limit of the scooter can be changed depending on the section of road they're riding on. So for example, if they move onto the pavement, the engine can be killed. If they move into a shared use zone, then the speed limit can be reduced. So that's the types of technologies that are coming out at the moment. In the 100 cyclist study, we basically gave 100 cyclists, well, originally planned to be 100 cyclists, but due to the issues with COVID, it's gone down to 60. We asked them to say near miss while wearing a panoramic camera, and then we extract those events from the audio file, and then we analyze the videos related to those near misses. So we first label them according to their type. So was it a person pulling out in front of them, a pedestrian walking out? Was it a close pass? And then we extract the risk factors. And we've used a variety of computer vision methods to do this. So this is just a couple of examples. So on the top right-hand side there, we have an example of a system that we created where we first detect the objects passing through the panoramic scene, and then when a vehicle comes within a certain threshold on this case, the overtaking side of the rider, we can flag that vehicle as overtaking. Note that this is not a close pass. We're just detecting this blue vehicle as overtaking within a certain distance, but we haven't set the threshold to be close in this case. The bottom image there shows panoptic segmentation. So that's extracting the objects within the scene and their outlines, so we can then get an understanding of the amount of the kind of density of vehicles and different road users in the scene, as well as the amount of road space and the surrounding land use. So we can do a lot with these types of models, but they're still primarily focused on what is there. They don't really have a real understanding of risk, and that's something that we can't really get just from looking at the images alone. So my last slide before I pass over to Nachpon, how do we go from these deep learning methods to actual improvements in road safety? And this is something that Nicola was talking about earlier. We found in our study that perception of risk is quite important. So it varies between people. I've been cycling personally in London for over 10 years. So an incident that I might not consider to be a near miss might be a near miss to someone else. And similarly, if you have a different level of experience, you may get into situations that a more experienced rider might not. So when we're recording near misses, we're also taking into account the demographic characteristics of the people who are recording them, combined with the factors that are present in those scenes. Generalization is needed. So ideally, we would like to be able to generalize from the factors that are present in those scenes to other scenarios, but that's quite difficult because, first of all, we've got the subjective side of it, who sees this as a near miss, who doesn't, and then the complexity of the different environmental, infrastructural, and behavioral aspects is very complex. So we need to develop significance of risk factors, but that's challenging. So as I alluded to in the earlier slide, we can use smart bike technology to help. So for example, we can improve our understanding of risk in real time. We can potentially alert riders to upcoming risks. This could be helped by vehicle-to-vehicle V2X communication. So if we know that there's congestion ahead, we can take decisions. But at the same time, bikes are supposed to be cheap and easy to use. So ideally, we don't want to have to give a bike rider all sorts of expensive safety technology. We'd rather just improve the environment that the rider is using. So safe infrastructure is always going to be the core issue. These types of studies help us to provide evidence on what is safe, but investment and also education and behavior change is important. So there has to be a will for people to want to cycle. And while we have these dangerous environments, people are unlikely to want to take up cycling as a viable alternative to their motorized or public transport modes. And I'll just finish with a quote from a paper which was looking at the role of cycling in two Asian megacities, Bangkok and Manila. So cycling is seen as a key option to achieve sustainable urban transport and public health objectives by policymakers and media. So similar to the European or the US context, there is a will to increase cycling. But however, the bicycle is often used by both the poor for short trips as well as the more affluent for sports, recreation, and fun activities. Sounding like a situation in London maybe 10, 20 years ago. So as a comfortable choice for transport purposes, cycling is still a niche and not yet an established culture. And when you look at the star rating in the earlier presentation, if there's no 3-star or 4-star roads for cyclists, then they're not going to cycle. It's as simple as that. Okay, so now I'm going to stop sharing and I'm going to pass over to Nachapon.
Thank you, James. I will start sharing my slides. Right. Thank you for having me today. My name is Nachapon Jongwilianulak. I am a PhD student in SpaceTimeLab for Big Data and Analytics Group under the Department of Civil, Environmental and Geomatics Engineering, University College London. Today, I'm going to talk about framework for motorcycle real-time risk assessment using onboard panoramic video by using deep learning for traffic safety analysis, in which this presentation is a part of my PhD works. I just would like to note that this study is supported by UCL Global Engagement Fund and Faculty of Engineering, Chulalongkorn University. And these materials in this presentation are submitted to 12 international conference on geographic information science and are under review. Here's the outline of my presentation. First of all, I will start with the challenges of analyzing and predicting road accident in Thailand, following by the related works. Then I will give a brief of dataset that I have collected in Bangkok roads. After that, I will present the proposed framework to assess the motorcycle crash risks, following by the preliminary results. Last but not least, I will discuss the future work and the potentials of this framework using AI. Traditionally, road safety studies are mainly focused on using historical road accidents datasets. However, in many countries or cities, records are either incomplete, unavailable, or underreported. Oops, sorry. Right. Underreported. And yeah, it's important to note that these datasets are primarily focused especially in Thailand, the dataset is not unavailable as well. And it's really important to note that these datasets are primarily focused on the accident that occur on highway that we've been using in Thailand. Yeah, so for the deep learning, especially for computer vision, has shown promise in enhancing and understanding of visual data. However, despite its potential, there are still some challenges that need to be addressed in this area, which I will discuss later. Right, so the progress of deep learning and computer vision has greatly influenced road safety research as computational power and hardware capability have improved. Researchers have increasingly utilized this technology as well. So initially, studies focused on using fixed camera at the intersections to understand vehicle, pedestrian, and infrastructure interactions, as Dr. Mongkol mentioned before. And the computer vision techniques were applied to track and analyze these intersections. For example, the static camera were placed at the intersection to capture critically conflict moments, as you can see on the screen. The computer vision, deep learning, and safety analysis were combined to comprehend the interactions between different objects. By integrating these tools, researchers can make informed decisions and develop effective strategies to improve road safety. And yeah, the limitation of static views has lead to study utilizing panoramic cameras mounted on vehicle parts or wearable devices. These studies incorporate object detection techniques and further analysis. The video on the right here demonstrate the potential of using panoramic camera on mobile device. It shows footage collected in Bangkok area that I have collected, which I will explain again in the following slides. In this video, we can detect close paths such as the white van on the right by identifying the moving objects and analyzing their relative speed and distance. This approach can be applied to various scenarios. However, the manual analyzing all cases developing the algorithm can be time-consuming. I will discuss our proposed framework later, which aim to address these challenges. So the dataset in this study was funded by Chulalongkorn University, which supported to purchase the equipment and facilitate me to return to Thailand last year. To collect data, I rented a motorbike and attached a panoramic camera on top of a helmet. The camera captured panoramic views while I rode along various routes. On the right, you can see the examples of how this video appears when unfolded. On the left, you can see the locations that I visited, which mainly include the routes from my flat in the north of Bangkok in Phaya Thai district to Chulalongkorn University. So we have developed a proposed framework for understanding motorcycle crash risks from using panoramic videos. The framework is divided into two tasks. First of the tasks is to understand visual to text, where we train computer to understand the visual context by describing what it sees using descriptive text. And the second task involves utilizing large language model. In this task, the computer is trained to analyze motorcycle crash risks by considering the road safety context using the set of descriptive text generated in the previous task. And in the visual to text task, we further divide into two subtasks. The first of all, it's the image to text, and second, it's the video captioning. These tasks have distinct difference in their objectives and computational requirements. First, the image to text tasks focus on understanding the static objects and the environments captured in the image. It's aimed to generate descriptive text based on the visual contents of the images. These tasks typically require less computational power since the images are static and do not involve analyzing dynamic elements. On the other hand, the video captioning is the task of generating descriptive text from the videos. It's aimed to understand the describe the moving objects in the video, such as vehicles, pedestrians, and its interactions with motorcycle that recorded the video. From the visual to text task, for as you can see, it's two tasks over here in the boxes. And in which you may heard or even use the ChatGPT, which is one of the applications of large language model. These models are designed to comprehend and process human language in different formats, such as written text or spoken words. In our plan, we intended to implement a fine-tuned large language model, specifically tailored to Thai road safety context by incorporating this context into existing pre-trained model. We aim to develop large language model to effectively understand and extract factors related to crash risks from visual descriptions extracted from videos. From our preliminary results, we conducted a test using large language models, large language and vision assistance model, comparing with manual supervision for text to image to text analysis without any tuning or specializing trainings. Our goal was to explore the potential of using existing visual to text model for road safety applications. For the results, the existing model performed well in answering questions, but it has relatively poor accuracy in certain classes, such as number of lanes, low surface conditions, and traffic size. These can be attributed to the use of panoramic images and the lack of fine-tuning the models to understand the Thai road context. For the future work, we need to implement and adopt existing visual to text video captionings and the large language models that are suitable for road environment and capable of understanding the road safety context in Thailand. This work has potential to analyze the unobserved motorcycle crash risks without having to develop cases by tracking relationship of boxes that we detected. And in the future work, as camera technology advances, it is expected that this framework will be able to operate in real time to notify motorcyclists of conflicts or any risks. Thank you for all your attention. I will conclude my presentation here. So, is there anyone have any questions?
I have a question.
Okay.
With the low accuracy of some of those attributes that you described, so the lanes and the road surface, can't you just supplement that through GIS databases that would give you those, automatically give you the number of lanes, for example? Obviously road surface is different, but could that be, you know, if you did like an ThaiRAP type assessment of that road and it was in there, could that be, could also supplement the accuracy of those videos? I was just thinking that you don't necessarily, I mean, the most important thing is about the behaviors and the kind of dynamic attributes. Just a thought.
Yeah, thank you for pointing that out. Yeah, I'm also thinking about using GIS dataset also, but it's not available in Thailand.
Yeah.
And the ThaiRAP is trying to collect those dataset for highway. And yeah, especially for urban context, like the road that maintenance by local authority, they don't have like that fund to collect these datasets.
Yeah.
So that
Okay.
yeah, it's still challenging for developing country.
Yeah, I totally appreciate that. Thank you, Nachapong.
So is there anyone having a questions for either me or James?
There's a question in the chat, Nachapong, that I can answer. So the question is about, can a GoPro camera detect cracks in the road? I think the answer to that is probably yes, if you use the right trained model. I think there's quite a bit of literature out there on crack detection. It probably depends on the size of cracks that you're trying to detect. So I know that in kind of engineering applications, you're trying to detect quite small cracks in infrastructure. Probably for road safety purposes, you're looking for maybe slightly larger potholes and things like that, which I'm sure you could detect. The 360 camera might not be the best for that because you'd have to deal with distortion first. So probably you'd have to transform the images first before you run that kind of detection. Otherwise, it might not work so well. But yeah, in theory, yes, it could work. The second question on there is something for you to take offline, I think, Nachapon, about the data that you could use in your PhD. But I think from what I recall, you've got most of that data already. Are you able to see that, Nachapon?
Wait, let me see.
I think it's behind you on the screen.
Oh, thank you for the suggestion. Right. I literally have contact to insurance company and already got the data set. But the reasons that why we started doing this, because the data set from insurance company doesn't have factors as such the data set from DOH. Yeah, that's why we are trying to understand the further context of what's going on the street without having any GIS data sets or good record sets of historical traffic accidents. Yeah, but thank you.
Okay, so I think we're just past 11 now. Could you just quickly put up the slide on the Global Engagement Fund, and then we can close for the online participants, and then I'll hand over to you and Garavig to sum up for the people in the room. Yeah, so just before we wrap up, I'd just like to, you need to switch back to the other screen, Nachapon.
Okay.
Yeah, thank you. Yeah, I'd just like to acknowledge the UCL Global Engagement Fund who funded this event. They allowed Nachapon to go over to Thailand to help Garavig to organize it, and also to pay for the venue. So thanks to them. They fund a range of small projects. You can see that they've helped over 700 UCL academics engaged with 600 organizations. So if you're part of an organization that might want to start up a small partnership with UCL, then do look into that. You can identify an academic within UCL. £1.5 million worth of funding has been allocated, but that's led to £33.5 million of additional external funding. So it's a good scheme for setting up things like this. So we're also, as part of this research, we're interviewing some expert stakeholders from relevant sectors in Thailand about motorcycle crash risk. And we're hoping to map out the risk factors according to the Haddon matrix, which you can see there on the right. So once that's done and we have our findings, we'll arrange another in-person and online event to summarize the findings of this study overall. So hopefully we can see you again there. So on that note, I'd just like to thank Nachapon again. I'd like to thank Garavig as well, and all of the speakers, and thank you all for coming. And I hope you all have a really nice day. And I'll pass back over to Garavig and Nachapon, and they can close the in-person session, and I'll stop recording now. So thank you again. Bye.
Thank you.